All right.
Okay, good afternoon, everyone. And today we are honored to have Dr. Glen Colopy as our webinar speaker. Glenn is the head of data science and statistics at Wildfell, a startup specializing in customer software and data science solutions for the biotech and life science industry. And Glenn's day-to-day work is as a hands-on full-stack data science contributor, focused on helping companies, usually startups, to succeed in their data analysis and AI initiatives. His focus lies in statistical machine learning with a particular interest in healthcare and life science. Glenn holds a doctorate in engineering science from University of Oxford. His work includes 2 patents in vital signs monitoring and many publications that are centered around medical machine learning. Glenn is a very active contributor to the statistical learning and data science section of the ASA. He actually is the recipient of our 2023 Outstanding Service Award. Glenn has been involved in the SLDS officers since 2015, initially serving as a webmaster before taking on the role of program chair. He also hosts data and science broadcasts and serves as a session editor for the Journal of Data Science. Without further ado, let's move to Glenn, who's going to tell us about Pareto principle.
Great. Well, thank you. Let me very quickly, I'm going to share my screen first and then start the slideshow just because I think it'll block me otherwise. Okay. So there's the slideshow. And I'll play from start. All right, great, cool. And you can see me? All right, sweet. Or you can see the slides, more importantly. Great, yeah. So what I'm going to talk about today is the applying the Pareto principle to data science. So real quick, if you joined this webinar because you want to see some new fancy models that you've never seen before, I can save you your lunch hour and you can do as you please. What I'm going to do is actually talk about how we can actually do more simple things. What are simple, highly effective ways to maximize sort of the value of data science? How can we be efficient and move faster and things like that? Yes, it does happen to involve some deep learning models and things like that because they have some nice engineering properties that actually do adhere to the Pareto principle or the 80-20 rule. And those are very nice technological advancements. But the purpose isn't to show off fancy models. The purpose is to show how people can be more effective and deliver more value to their companies, to their customers, and things like that. Because I think that one thing that we've really seen is that the shine has worn off for a lot of data science initiatives. People have seen their data science initiatives lose money for the company or provide zero ROI, and people have gotten savvy to that. So it's time to adjust and see and inspect ways that we can become more efficient. So just the quick outline, I'm going to introduce myself a bit. Then I'm going to show you 2 data science projects, followed by introducing the Pareto principle, the 80-20 rule, and we give them plenty of examples. So as Jihua said, basically I come from a stats probabilistic engineering background, so a lot of Bayesian non-parametric work and things like that, mainly in healthcare and the life sciences. And I've been pretty involved with the ASA and SLDS section. I also have done a podcast, which I think probably quite a few people have seen, or if you haven't, maybe you haven't missed out that much. But basically, yeah. So basically, if you just want to think of me as a data scientist with an engineering and probability-based background or machine learning-based background. And my day-to-day work is basically I co-founded a startup, a software company, and I think mainly the point that was worth noting is that unlike for those who sort of consider data science to be a role that's predominantly, say, data analysis and model development, the key point is that for my job, actually, it is very heavily based on a full stack data science role. So effectively from data acquisition, from the software, from the hardware, designing the data acquisition methods, all the way through the pipeline, data cleaning, and then essentially like model development, model deployment, and then basically putting those model outputs like AI outputs and delivering them to clients in a way that's useful, particularly for a lot of R&D type work or customer facing models. But yeah, basically we have two sort of sides to this. We actually develop our own software that we sell, and I think that's important because basically many people in the data science field tend to be several degrees separated from the actual product of the customer that their company is facing. And one thing that essentially our clients like, the startups, is that we have direct experience pleasing customers by the software that we develop. So we aren't removed from it. It's not theoretical. We do this ourselves. And then obviously we do data science consulting. And for what it's worth, consulting to me doesn't mean, basically sitting around in a suit and tie saying, oh, you ought to do this or they ought to do that, and then letting somebody else do it. This is roll up your sleeves, hands-on development and building cloud infrastructure, building the models and deploying them and everything like that. So extremely hands-on work. Sweet. Now, some background projects. I'm going to introduce you two background projects. The first is in hospital patient monitoring, so vital signs, and this is using Bayesian nonparametrics to monitor patients' vital signs in real time and provide inference. And the other one is on hydroponic crop hardware monitoring. So effectively, we have these hydroponic systems. People need to eat, plants need to be eaten, so we eat them to keep the plants in line so they don't rise up against us. So basically, we have a hydroponic system example where we're both monitoring the crops and the hardware. So essentially, the hardware that acquires our data and the actual data itself. We're trying to monitor both of those. And the reason why I'm going to show you these two background examples is, one, because obviously everyone likes to see some machine learning in action, and that's fun. But also, these are going to be the baseline applications for our Pareto principle examples. So effectively, I'm going to show you some applications, and then once you're familiar with those, we're going to re-examine those about ways that you could essentially more efficiently execute some of the delivered value on those problems. And I hope that these examples are pretty fun, and they provide some sort of at least like mathematical or domain conceptual. I hope it'll be gratifying on some level that essentially you'll understand a little bit more why some of these more simple approaches work sometimes, and perhaps you can use those for your own work. So we'll hop into the first one, which is patient monitoring. So the patient monitoring, the first thing that we're looking at is the hospital setting. So for people who've seen, for example, hospital dramas on television, essentially the scenario that we're seeing is something like a step-down ward or an ER. Those are merely two different things for people familiar with hospital care. But the idea is that we have a hospital ward with numerous patient beds, and the nurses and the doctors go around monitoring them, typically nurses, and they will do things like record the patient's vital signs that they see on a screen down onto, for example, a chart or something, and make some type of clinical inference from that. So they're already using data for clinical inference. But there's already essentially a disconnect in what's going on here, because essentially while the nurse is seeing an individual data point on this monitor, what in reality is happening is that there's this rich tapestry of time series data behind it. So essentially the clinician sees a snapshot of time on which they make their decision. But in reality, there's this huge time series data that's essentially being thrown out and not being included as part of clinical inference. In part because humans aren't very good at dividing or inverting, matrices in their heads and things like that. So there's computational problems, and there's also basically just inferential and contextual challenges. So as we said before, essentially the clinician's data is something like this. So they'll see what time it is. They'll see the current heart rate, respiratory rate, that's how fast you breathe. SpO2, that's blood oxygen saturation, so how much, essentially how well your blood is delivering oxygen to your body, things like systolic and diastolic blood pressure. And in reality, there's this rich time series behind it. And to this quick snapshot, the clinicians actually applying a decision rule, a very dichotomized decision rule. Something like this. This is the National Early Warning Score. It's popular in the United Kingdom and some other Commonwealth countries, where essentially you have a score and it's just, your heart rate. Is it between 50 and 90? Is it below 50? Is it above 90? And they essentially dichotomize each vital sign individually and sum it up as a score. And the intuition behind this is that healthy people have average vitals. So essentially you're expecting them to fall somewhere in the middle. Sick people have more extreme vitals. So as you get sicker, your vitals deviate from normality. And of course, dead people have no vitals. And so the idea is that as people become sick, you want to catch them as those vital signs become more extreme. And that is essentially your early warning score. But what's missing here is many things, including personalized expectation, the time series component. So effectively a heart rate that goes from, let's just say 60 to 100 in 1 minute is not the same as a heart rate that goes from 60 to 100 in 2 hours. Those are two very different things. Those are two different pieces of inference. So we have a lot of information that's not being included in the way that clinicians currently make decisions. So the idea would be here, and there's also a lack of personalization. So you can have the idea that the staff is monitoring a current vital sign. And for one patient, this might actually be fairly expected. So this might be a completely appropriate time series or set of data for one patient. But for patients, for like the second patient, but for patient 1 and 3, other patients, this would be very dangerous data. This would be not data that's expected. So for example, we might want to have these bounds, and this is just for what it's worth, the Gaussian process, but these bounds where it actually quantifies where you'd expect an individual patient to be at a given time. And then if we can use those as a reference, then we can decide whether or not a patient is healthy or not deteriorating. Obviously, these are hospital patients. No patient is healthy when they're in the hospital. But basically, it provides a useful probabilistic reference about what the patient's current state is and how acutely ill they are. So one possible solution that provides a nice, robust Bayesian non-parametric example is a Gaussian process. So the idea is that we can fit a Gaussian process to the time series. The time series autocorrelation, so essentially the correlation across different time points and also across vital signs, for example, are captured in that covariance function. Since it's Bayesian, we have access to priors that can regularize our hyperparameter fits. And we can also use that to incorporate expected dynamics. So essentially regularize how fast a patient's heart rate plausibly could change. And we can incorporate that physiological domain knowledge into the model. And another bit is that essentially the parameter inference, whether that you want it to be something like MAP or MCMC slice sampling, choose your inference method of the one you prefer. That is what allows us to essentially personalize an individual time series to a new patient. So effectively, you can take this this prior distribution, and by fitting it to an individual time series, you essentially now have an individual patient model, which is quite interesting. Did you have any questions? Was there a question yet, or are we good?
We are good.
All right, cool. So once we've fit these, so essentially once we have a Gaussian process fit to the time series, so what we have here, for example, is here's the Gaussian process's posterior mean. It's fit through the time series, and then we have this the posterior. I think of it basically as like a shell. It forms a nice shell around the data. But there's the variance around the mean function. And the idea is that we can fit this to data, and then we go from having many data points to essentially just having a distribution. Now, of course, it's a multi-dimensional distribution, but still distribution. And we can do things like take this new distribution fit to a new patient and compare it to a dictionary of healthy patients. So the idea is we one by one compare the new pattern to this dictionary of healthy patients. And if a new patient doesn't look anything like any of our healthy patients, well, then that might be a piece of evidence that the patient is not healthy. Whereas if we compare this to, for example, a dictionary of unhealthy patients, well, then that'd be evidence that the patient is healthy or is not healthy. So again, the idea is that it takes this, like high dimensional, high frequency time series and compresses the information into essentially a nice manipulable distribution that we can then perform, information theoretic comparisons to, something as simple as like a KL divergence on a multivariate Gaussian. We can do things like that and have a nice essentially inference or reference for how far this patient deviates in the time series sense, as opposed to an individual point in the time series sense, how much they deviate from a population of healthy patients. And another thing that we could do is, and I like this one because you can see the time series jittering some as it fits and refits. So effectively there is this active inference, and there's times where it becomes a little bit uncertain based on the data that's coming in. But the idea here is that the model is constantly fitting to the time series and forecasting forward. That's the yellow, that headlight is a forecast forward. And what we see here is that the forecast, for most of the time, obviously the data fell within the forecast. The data that was coming up fell within this headlight. But then we reach this point where the data falls outside of the headlight. And this is a key example where essentially this probabilistic approach that we have can turn clinical inference on its head. Because in this case, a patient's heart rate dropping down from 135, which by the way is a very difficult heart rate to reach unless you're exercising, so you're at 135, and then the patient drops down into about 120, 110 over about an hour. And if you're just comparing individual points, saying, oh, well, 135 is extremely abnormal, 110 is more usual, this is therefore the patient getting healthier. What's interesting about this time series, probabilistic time series, it's actually saying, well, this is actually quite a large drop. It's more than you would expect given the variance of the time series data that we've seen so far. So it would actually invert the clinical inference and say this drop is actually too fast to be healthy. We should flag it and bring it to the patient. And so that's again a very nice example of a time where you would at least want to bring this to a clinician and say, no, this is possibly not a patient getting better. They might be getting worse. They have this unexpected drop in heart rate. We should check something like their blood pressure or what else might be going on. So the result of this is that basically when we have these types of methods, we can have things like earlier warning in advance of deterioration. So this isn't something that I'll really get into, but it's not about necessarily just classifying when a patient is sick. It's actually about giving them a clinician enough early warning that you can then have a clinical intervention and save them. We also have fewer and more concentrated false alarms. So effectively, persistent false alarms are something that really distract nurses. And so it's nice to reduce them. But another thing that's nice to do is concentrate them. So effectively, they're only happening the same time. So essentially, if you had an alarm once every minute for an hour, that would just be annoying. But if all of your false alarms went off at the same time, that would be possibly more helpful depending on the clinical preference. Because if they're concentrated all on one patient, then you're only distracting them once per hour on something as opposed to once every minute. Or they then begin just ignoring the alarms entirely. And another useful thing is that there's an explanation of the alarm source. So when we have models like this, where we show what our expectation is, it's probabilistic, but essentially people understand expectations and expected bounds and things like that. You can explain why you're alarming. And so even if it's incorrect, the context there would mean that the clinician wouldn't lose faith in the overall alarming system because they're seeing why it's alarming, and they can choose to ignore that alarm, but they can at least understand that it's not just a completely random occurrence. So those are helpful things. So That is, those are some of the benefits of a good, robust Bayesian non-parametric approach. Cool. And now I'm going to move on to the second example. So of course, we'll be coming back to the patient monitoring example when we look at the 80-20 Pareto rules. But now I'd like to quickly go through the second example, and this is plant health and hardware. Oops. So what these people right here are oohing and eyeing at is an indoor farm. It's an indoor farm provided by Leska Life. That's one of my clients. And it's local food in a controlled environment. I believe this one is based in Beijing. But basically, the benefits right off the bat of indoor farms: year-round crop production, so it's independent of weather, independent of climate. Reduced transportation costs. And so basically, if you're growing food locally, you don't have to move it as far. A lot of us get lettuce from California, regardless if we're in California or in Maine. Oh, Jiho, did you have a question? Yep.
So can you see the question in Q&A?
Oh, sorry, I didn't. Oh, let me open it. Okay. What is MAP? Oh, sorry. Oh, I guess MAP, two things. So there would be mean arterial pressure was MAP on that one. So that's essentially, it's a combination of diastolic and systolic. Sorry for not seeing that earlier. I'll keep the Q&A up now so I can see it. Cool. Yep. So that's she was referring to the image before where there's a nurse monitoring multiple vital signs, and MAP was one of them. And that's just my way of taking multiple vital signs and turn it into one time series. Yeah, cool. So back to the plant growing question. It's also more water efficient, so 90% less water than traditional farms. So for example, this might not seem like a big deal to a lot of people, because you turn on your faucet and you get water. But if you look out west, huge drought issues and lack of water there. I believe China over the last year, for example, has had several large drought issues as well, where effectively, if you looked, maybe the Yangtze River, I might be getting that wrong, but effectively, you can actually look at a satellite image of some of these major rivers in China, and they were, flush and green a year or so ago, and now it's very dried out. And so effectively, there's a place where even a place like China, which has access to water, you'll have an entire region that now has extremely reduced access to water. And then that's not even bringing up places like Japan, Singapore, the UAE, Saudi Arabia, where these countries, by being islands and or in extremely arid regions, won't have as much access to water. Water then is at a premium. So what water efficiency is in many places at least as important as energy efficiency for example, growing plants. Other things like nutrient efficient, fewer fertilizers in the waterways. So essentially that giant bed of algae that goes from Brazil up into the Caribbean and Florida each year. Great for sea turtles, really smelly for tourists. There you go. Like it's essentially fewer fertilizers out in nature is probably a better thing than not. Pesticide free as well. So anyway, there's a lot of benefits to these. There you go. But they also have their own costs. So essentially, a lot of these are small farm operations. So effectively, they're operating on lower budgets. Skilled labor, farm labor is extremely skilled and it's expensive. It's the majority of so it's the single largest item of cost item. Also, skilled labor is becoming less and less common each year. And there's catastrophic risk of loss. So for example, if a single crop dies, for example, if a farmer comes in and finds their crop dead in the morning, that's tens of thousands of dollars that they're out. So we'd like to mitigate those. So I'm just trying to see my time. I just realized I don't actually have my phone on to see my time to track it, but I'll just continue on. So basically we have, our solution is basically a multispectral image. And just real quick, human beings see in RGB, That's just what our biology allows. Multispectral means essentially across and beyond the visual spectrum. And what this does is it actually picks up a variety of other basically biosignals from the plant. So whereas RGB will only pick up certain biosignals, we can pick up far more with across the spectrum. So our solution is something like this. We want to be monitoring both the plants and the hardware health with these multispectral images. So the idea is we have these cameras over the plants, and it's monitoring them, taking these multispectral images, HD, and then we can basically have a dashboard for monitoring the plant's health. So essentially giving the farmers, the grow operators, access to real-time information about the health of the plants. Doing your walk through a farm can be very long. It takes up a lot of time. And so effectively, if you have full-time viewing of this, then it saves a lot of hours. But we aren't just monitoring the health of the plants, we also need to monitor the health of the hardware. Because if the hardware goes down, then our inference about the plant's health isn't really worth that much. So we are also doing dashboarding for hardware monitoring. This might be essentially looking at how unusual a signal or a sensor is. This is sensor data like environmental data, but it's also essentially using cameras to decide whether or not the images to decide whether or not the camera is functioning properly. So we need to be essentially alarming and making people aware of both these things. Are the plants healthy, and is the hardware itself still continuing to operate? So a quick example, this is something like image quality scoring, where and this is actually pretty an initial 80-20 example where there's a lot of complex computer vision models that we can have for the anomaly of data. But there's also, you could take an image, break it down by its statistical features, and you create an anomaly detection model that way. Something as simple as plopping a kernel density estimate over statistical features of the image and flagging the ones that fall far out from what might be expected. So here the idea is the image comes in, you calculate the statistical features, you compare it to an anomaly model. So effectively, if the model is far away from where there's high density, then that's evidence of an anomaly. And then of course, we'll just use the traffic light approach of green is good, red is bad, yellow is sort of something in the middle. On the plant side, we can do something a little bit similar, where effectively, for example, we can take the same plant image, and we can take features like the biological contrasts at different wavelengths. And you can, for example, aggregate weak labels. So basically, if plants absorb light as part of photosynthesis, and of course also they reflect light that's not being absorbed. And so the differentiation between those what the plants reflect is actually representative of the plant's photosynthetic activity. You can basically tell what the plant cells are doing based on what is reflecting at which wavelengths. And the idea here is that essentially you can track photosynthetic activity quite easily. And for example, if you see it rising, there's more photosynthetic activity, the plant's healthy. But if you see it dropping, then that's something to be worried about. So here, what we can see is that with a simple method looking at photosynthetic activity from the plant, so these are just really simple statistical methods, no fancy computer vision yet, we can pick up when the plant is healthy, and then if a drought hits, we can see it drop off. So effectively the plant dies off over time, and we have that real-time signal. Again, what you don't want is for the farmer to come in the morning and find all the plants like this. You want the signal, wake somebody up, get them out there to fix the plants and get them healthy again. And I guess the bit that I also want to say is, the work that we're doing, it doesn't just end, and I'll walk you through the thing in a second, but the work that we're doing doesn't just end at creating a model and deploying it. The idea is that we're handling the ingestion from the hardware, the data processing, the data storage, and things like that. The machine learning that does the label, and there's multiple models here that you have to essentially keep in operation. The whole purpose of ML ops is how do you essentially keep multiple plates spinning at different times and keep your models up to date and performant. And so we might have things like labels for farm activity, labels for hardware activity, and also data science labels. So labels that are really only of interest to the data scientists or machine learning engineers who are doing these things, and not necessarily of interest to the end user. And what's interesting is with these ML labels, essentially, if it's uncertain what a label might be for one of these tasks, you can flag it as uncertain. Or if it's clear, you can just pop into the database. And what's nice about what we've done is we've actually managed to connect the loop, and we have when the model identifies that it's uncertain about what the label should be for a certain task, we have a UI that allows an expert to label that data. So we're essentially completing the loop that as unusual data comes in, we can start adding that back to the data set without it throwing everything off. And then, of course, we have a platform that lets people view this and interact with the data and things like that. So the bit that I want to show here is effectively, it's not just about the creating a model and letting it sit somewhere. There's an entire ecosystem that has to be supported in order to deliver value from this. If these models are just created and sat around, they wouldn't be any good. Or at least they wouldn't be useful. They'd be good at their task, but not useful to anybody else. All right. So now we'll get on to the main part. I know we're 30 minutes in, but with these examples, I'd like to show you some things for the Pareto principle for data science. So really quickly, the Pareto principle wasn't actually developed by Vilfredo Pareto. It was actually developed by Joseph Urine. He was an engineer, or Jurin, and basically is based on Vilfredo Pareto's observation that roughly 80% of consequences come from about 20% of causes, and he calls those 20% of causes the vital few. And what one of the examples that he had was that approximately 80% of the land in the Kingdom of Italy was owned by 20% of the population. So the visual of this is approximately the entire boot of Italy is owned by 20% of the population, and then the two islands, Sicily, and unfortunately the other one is not popping in my head right now, would be owned by 40% each. And now I'm feeling embarrassed because, but yeah, so effectively all this land mass is owned by the minority, 20%, and then these two smaller islands are owned by 80% of the population. Now it's going to bother me what that second, the non-Sicily island, is for the rest of the presentation. Yeah, so basically there's plenty of other examples like this. The idea is, 80% of sales come from 20% of clients. Here's the distribution of the GDP, world's GDP. And it's basically just a power function. 20% of the most reported bugs account for 80% of the crashes and things like that. The time it takes to develop software is 80% of the time it takes to develop software is sorry, 80, the island thing is really distracting me. I can't help it. But yeah, 80% of software is
already told you in the FQ&A.
Oh, Sardinia. Thank you. Yes, that's it. Yes, there we go. Thank you. I appreciate that. Okay, now I can move on and only be embarrassed, but not distracted and embarrassed. So I appreciate that. Sardinia. Yep. Cool. All right. One example that I like that I think relates to a lot of people is that if you think about an airplane, 80% of the toggles might be something like the little air valve that lets you adjust the AC for your airplane seat. But 99% of whether or not the flight was good aren't those toggles. It's this thing that's happening in the cockpit right here. And so there's, I think, a nice dramatic example of, and admittedly there's a lot of buttons there too, but the idea is there's a lot of things that you can toggle, but only a few of them really matter. And for data scientists, I think what's important is that there's this idea that a large part of your output will come from a small subset of your skills. So for example, being really good at exploratory data analysis, EDA, or really being good on a specialist data type. Those are the places where a large portion of your output and value will come from. I'd also say that a small percentage of your results will be the majority of the value that you add, for example, to your company or to a client or to a customer. And essentially, a small concept can basically a small number of working concepts or principles can be what propels your team. Or in many cases, what I've seen in startups, a small number of data scientists are doing most of the valuable work on a larger team. And so strategically, what this means is that a lot of your time is wasted if you aren't good at prioritizing how to spend it. So what you should probably try to do is take that best 20% and do it 5 times in a row. Now, of course, that's hard. And even if you succeed at that, it means that then that 100% of your time, even within that, the 80% of that now new value would then be done in 20% of that work. So there is something where, even the tail end of the tail end of this added value seems to persist. So my TLDR on this is that basically your data science and AI approaches have trade-offs, and you need to prioritize what you're going to work on. So I like this idea where effectively you can choose between have something in gold or something in silver. The problem is the thing in gold is super spiky. Like, it's going to be tough to handle that one. Do you settle for a big lump of silver that might be worth a little bit less, but it's way easier to handle? And so those are the type of trade-offs that I think people should be thinking about. You decide which problem is most important. If you're solving a problem that's not important for a client, for a company, or for saving somebody's life, if someone doesn't have oxygen, they probably don't care whether or not you're monitoring their heart rate at the moment. So it's something that you have to decide which problem must be prioritized. What and how to model. So effectively, the how one I think is actually quite interesting. Or effectively, like statistical inference, a lot of statistical models. You need to figure out which inference method you're going to be using. When you're approaching a new problem, what should you be learning and how should you be learning it? So what are you going to prioritize about a new domain so that you can get up to speed quickly? And also where to specialize. Because I don't get into it too much here, but if you look at the job market for data scientists, a lot of the work that's being demanded is for specialist positions right now. And the reason for that is that if it's not specialist, somebody's already done it. So effectively, when people are looking for new hires, they're looking for people who can really, perform well in a niche topic. All right. So now on to the examples of 80-20 for data science. I'm going to give us a quick roadmap here. We're going to do a speed session. So I'm going to do some statistical concepts that I think have an 80-20 value. And because of the audience, I'm just going to zip through these because you basically know them, but I would just like to confirm them as 80-20 value. When I present to other audiences, I actually belabor these statistical ones because they aren't as familiar with them, and then shorten some other things. But yeah, basically, I'd like to show you some statistical concepts I think have 80-20 value, ones that we take for granted, but they're quite valuable. Then I'll show you some 80-20 tools, which are basically just hacks. And I'm just going to list a few of those and go quickly. But then we'll get on to the main event where we'll go back to those initial applications, and I'll show you some places there where we took an 80-20 approach and derive some benefit faster than would have been taking an inefficient approach. All right, so some 80-20 statistical ideas, which are things that this group pretty much already knows. So we have a few here. They're pretty common. Correlation does not equal agreement. I know a lot of people like to do correlation does not equal causation, which is also true, but I like to do this one, correlation does not equal agreement, because that one tends to catch statisticians more a bit, or people working data science more. We like distributions, not point estimates. Simpson's paradox, I think, is a nice 80-20 concept. It's a simple concept that gets you way farther ahead than someone who's not aware of it. And then dichotomized and continuous variable. So real quickly, correlation does not equal agreement. You could have these two measurements of the same thing, and there's measurement X and measurement Y, and those two measurements could be 100 like perfectly correlated or 90% correlated. But the fact is that doesn't necessarily mean they agree. For example, X and 2x are perfectly correlated values, but that doesn't mean they agree. One will always be twice as much as the other. So that's why we have things like Bland-Altman plots that actually look at the bias and the offset of agreement. How much do these things disagree? So again, this is just a super bog standard statistical example that statisticians are aware of. We're used to dealing with these things, but non-statistical, non-data science people tend not to be aware of these things and make that same mistake, just in the same way that they might mistake correlation and causation. Correlation and agreement, that these two measurements are highly correlated, doesn't mean that they agree. Distribution is not point estimate. So again, this is something where you might have someone say, well, I just give me the median value of this distribution. And while that, two distributions could have the same median value, but extremely different characteristics. So here's an example of a Gaussian distribution and a gamma distribution with the same median value. But the vast majority of the weight and the probability between the gamma is offset. It's much farther to the left than the Gaussian. And so what we as statisticians know is that you don't just want a point estimate. You have to appreciate an entire distribution for the effect that it might have. And a simple example of this is an effect of what it's like on a normal day. You don't want to know what a normal day is like. You want to know what an outlier day is like. For example, here's a normal day on on Wall Street. Like everyone's just sort of chilling out. They're getting their nice money from quantitative easing or whatever, and chilling out, having their coffee. And then there's the day where everything goes to hell. And the thing is, we don't design our systems around those average days so much. What we really care about is avoiding those really bad days. We don't want to lose all our wealth in a single few bad days of trading. So effectively, in many cases, we don't care about the average. We care about the outliers and protecting ourselves from outliers. Another quick one, Simpson's paradox. Everyone knows this one. I won't belabor it too much, but yeah, sometimes things are more complex than they seem. So don't forget to add in variables that matter, or sometimes they're less complex. And I think Simpson's paradox is one of those ones where, again, it's a mental pitfall that a lot of people who don't look at data fall into, but where we can add our values that we are aware of these types of challenges. And obviously, Simpson's paradox, no one even thinks it's a paradox. It makes perfect sense, but you just have to be aware that it's out there. And then there's dichotomizing a continuous variable. So I think it's Frank Harrell talks a lot about this, saying don't do it. Andrew Gelman has a really good picture. I couldn't find it. I'll keep looking, of essentially a spline model where it just, there's this complete disjoint in the probability where going from X at one point to the next just has this massive drop, and it makes no biological sense. But when we're dichotomizing our continuous variables and things like that, we fall into those sort of traps. Random forest models are famous for dichotomizing continuous variables. They have nice performance sometimes, but still fundamentally they're dichotomizing these continuous variables. So you need to be aware of those types of things and figure out what you can do to alleviate any of the problems that can be there. So here's my dichotomized continuous variable where you just have a completely disjoint spline as you go up that makes no actual sense. Cool. Now I'll go on to the tools, and we'll go through this section even faster. So obviously there's a huge suite of R and Python productivity libraries. I don't want to belabor these, but I think a lot of them, people know what they are. These ones that will clean up our notebooks and provide nice automated initial statistics and things like that. Taking your notebooks and popping them into PDF format, or putting them in, making them conducive to LaTeX, things like that. Another one I found interesting is ChatGPT or Copilot, which is similar for essentially LLM assisted, large language model assisted coding. If you look at the price of the premium, the monthly subscription to ChatGPT, I think it's like $20. And if you look at the average US salary data scientist, that's about, it works out to, by my calculations, depending on how much vacation you take, about $56 an hour. And so for the average data scientist, you only need to be saving about 3 hours per month on this, which for some people who use these models quite efficiently, you're saving a few hours every day by using these methods, for example, to help accelerate your coding speed and things like that, or debug some problems. Now, of course, as some companies learned the hard way, don't put in sensitive information to ChatGPT. They suck it up like a vacuum, and it'll be there forever. But if you're smart and diligent, you can accelerate your time without hopefully exposing yourself to too much risk. AWS SageMaker is actually another interesting one that I'm not sure, depending on where you're working, how much this matters to you. But for example, essentially, it's essentially you can do your notebooks in the cloud on AWS, Amazon Web Services. And some of the nice things are that you can have your notebooks and literally just change out the size of the compute instance that you're using. So say you want to do some EDA and develop on something small. And then afterwards you have this model that you've developed, like a simple one. Now you want to run out a whole bunch of data. That's just 2 clicks away on SageMaker. And for a lot of applications, I've been in times where head of engineering and I have literally sat down for about 4 hours trying to debug some connectivity issue where we're, for example, trying to run something on an EC2 instance. And the added cost of using something like SageMaker, where it's already hosted, is absolutely worth it in those cases. So I think those are cases where effectively, if you're not going to be running things locally, or you're looking to run things in the cloud and have access to speed, it also does things like feature stores and things like that, where learning these simple skills can actually vastly accelerate what you do. It doesn't waste a whole bunch of time. And I know that those aren't cool data science-y topics to discuss, but they do warrant some discussion where effectively, if you can be saving a huge amount of time in these edge cases, it's definitely worth considering. And the final one is, talking about analysis versus dashboards versus alarms. So one thing that I point out is that, when we're working with clients, the initial analysis that we do might take them hours or days, might take us, hours or days. And that's going to cost them hundreds or thousands of dollars. When you bring that to a dashboard, then those costs then get shrunken down to minutes. And that's maybe tens of dollars, and including person time and compute. And then when you automate that further and you have an alarm system, we're literally down to milliseconds and fractions of a cent that it take to run these things and get that same that information. So effectively, the cost per insight for these things drops drastically as you add sophistication to these things. And something like an analysis and a dashboard and alarm pipeline, those aren't difficult things. I wouldn't consider those to be extremely advanced. So it's just basically you learn how to deploy pipelines, you learn how to deploy dashboards and alarm pipelines, and go from there. But I think there's a lot of value in these things that obviously they aren't going to be covered in advanced machine learning conferences, but they add a lot of value to what people are doing. Another one, basically just, I thought this is another 80-20 idea. It was just the idea that even, because there are concepts that can make your time better. And the idea is, for example, that you might know that you need just to focus a bit. So essentially that 1 or 2 hours a day of focus might be the best work that you do all day. And if you don't get that focus, then you're not going to be productive. And I've seen this pitfall a lot. It's especially attractive in grad school when there's so many distractions. And so the idea is that you need to find yourself a place to focus. And it doesn't matter if it's a cramped under the stairwell Harry Potter office. You need to find your time and focus. So again, this isn't a tool or anything, but it's just an idea that if you understand this concept, that a lot of your value might come from a very specific part of time, you should be very protective of that. Cool. All right. Now we will go on to the main event, which are the examples of in projects. So now we're going to go back to our the initial data science problems I talked about, and I'm going to show you some 80-20 examples from that. Oh, first, actually, I'm going to show you one from NeurIPS, just to show that I'm not the only person doing this type of stuff. So here is this is by Scully et al. It's the hidden technical debt in machine learning systems. This is a paper that everyone should read. It doesn't matter if you're in academia or industry or a student or whatever, because basically it really helps clarify this important point that I think a lot of people miss out, which is, yes, as you squint to see that little black square in the middle, that's your ML code. And so effectively, for actual deployed real world machine learning systems, we spend so much time thinking about the models and how to optimize these models, but it's actually a very tiny part of these overall systems. It's again one of the reasons why so much of my work is literally on building out the other infrastructure and support systems that happen around the ML code, as much as I love building machine learning models myself. But I think this is important because it basically says that we who focus so much on the models, you might be focusing on a 5% of the total problem and spending all your time on 5% of the total problem when there's all these other things that need to be addressed. And if you do that, your time might not be as well spent. Or you need to find yourself a team where all these other things are handled, and therefore you are adding value by spending all your time tinkering with machine learning models and developing AI systems and things like that. Cool. Now we'll go in from patient bioscience. So everyone recalls back where we had this one, where we had this nice Bayesian Gaussian process, fits it to a time series. It's regularized, we have these patient-specific priors, and it forecasts forward and finds that, what's in the forecast is far different from what was expected. And that's cool, and it's robust. And that gets you patents and things like that. But an alternative thing, though, is that we could have also just taken this window right here and taken a window right here, fit a super basic univariate Gaussian to it, and compared those values. And you would have gotten a really strong signal as well, right? So like you could fit this infinite dimensional Gaussian distribution, forecast forward, learn how to do all that robustly. Or you could have just taken two small windows and compared them over time and gotten probably the same signal. So, not always, like there are a lot of pros to this system right here. For example, that it is time and covariate adjusted. So effectively the Gaussian distribution at this point is different from this one. Each individual data point has its own specific Gaussian distribution to which it's compared for anomaly. And if there's a nice steady trend that the Gaussian process has learned, it's adjusting for those things. As I said before, it gets nice patents that pay things. But there's also things like the challenge of prior selection in building the model and the automated inference. Automated inference is nothing to, automated statistical inference is nothing to sniff at. It's one thing to fit a model by hand and leave it in place. It's another thing to entrust a machine to be constantly refitting a model and perform well. That's a much higher level, much higher standard of robustness. In contrast, basically, if you just took this little section right here, this one that I'm, this data in the blue, fit a model there, take this model data in the red, fit this model, that's an embarrassingly simple thing. But I promise you, this method has been used at basically every place I've worked. So there's the model that gets a patent that pays well, and the model that I haven't gotten anyone to care about ever. But I promise you, people use this little thing everywhere. It's like a pocket knife. It's just super useful, or Swiss Army knife, I guess. Cons, obviously it struggles with edge cases where autocorrelation is important. In a con, it's embarrassingly simple. Like I'm embarrassed sometimes to be like, no, I just did this model because it works pretty well. But yeah, and I also say this, one other pro of this model. I had to go through this Gaussian process model, all this fitting and the automated inference and things like that, to realize that this model works well for many cases. So effectively, this complex model, when I compressed it down, gave me the idea of how I could do some of these things simpler, and I can understand what the edge cases are. So this isn't a repudiation of complex approaches, but the question is, once we've done those things, what can we learn from those model successes such that we can then make something simpler that works in a more nimble way? This one you can also feed into another machine learning model way easier too. So effectively, it'd be one thing to fit this model and take these outputs and feed that into another model versus this one. This is a much simpler feature to feed into another part of the machine learning pipeline. Another place where you don't need AI. So effectively, we had this one where we take this shell of what the patient's time series is, and we compare it to, a large number of reference patient distributions. And that's cool and it works well. And it's nice to have comparing entire time series versus a single point. So a single noisy point versus this entire well-fit regularized time series. But you also don't always need a complex algorithm for that. Like, for example, would it have sufficed just to learn the individual patient's overall IID distribution and flag when that patient falls out of their IID distribution? So effectively, we take this patient and we just literally accumulate all their data and update what the distribution is. So essentially, as each data point comes in, we just refit a simple univariate distribution and flag anomalous data there. Because one of the things we can see when we group the data by patient, so effectively along the x-axis right here, we have individual patients. And what we can see is that individual patients pretty much stay in very confined ranges. So even while vital sign values as a whole are well spread out, so there's a very wide range of population-based vital sign values, the individual patients occupy extremely small areas of that. So what do you learn from that? Well, if we just know that individual patients range, then we just flag whenever they sort of come to when they're doing something unusual with respect to their own range. Another useful thing to realize in this is that imagine you had to set an alarm threshold to alarm on sick patients or deteriorating patients. If you set an alarm threshold right here, well, you're going to be alarming on a tiny fraction of the patients, and all these patients here are going to be neglected. So if you set an alarm threshold at 110, all these other 175 patients basically have no chance at ever getting a high value alarm. So they could be someone with a natural heart rate of say 50 or 80, and you're never going to have an alarm on them, which means they're going to be neglected. They could deteriorate out from under you, and you're never going to see that because you're busy out here looking at a population-based parameter when you could just do a simple grouping and have a patient-specific model. So there's another one where effectively you can do something very simple, and probably 80% of the benefit of this model, or 80% of the benefit of personalization can be done in a simple model. And then if you want something more complex, you can build that up. For the plant grow operation, so these are the final two examples. And this one deals with the issue of incoming data with new classes. So the idea is, a farmer doesn't need AI to tell him what crop is which. Like, he just doesn't need that. If he's worth anything as a farmer, he does not need AI to tell him the difference between a butterhead and a green rosa lettuce or a romaine lettuce. In fact, all of you with about maybe 30 seconds of studying could actually memorize these different crop types and then sort this thing with very high accuracy. But the AI might want to learn these things, what crop it is, because it's useful context for what's happening in the grow operation. So effectively, if someone comes in, a farmer comes in and takes out this first tray right here, and they replace it with this tray, that's a useful piece of information that probably some harvesting or some transfer of the plants is going on. So the farmer doesn't need to know this, but the machine would like to know this because it helps it keep track of the activity on the farm. But while we know what crops have been currently grown, so what our current farms are doing, we're rolling out to new farms, and those farms have new types of crops. So what do we do here? Should we be retraining our computer vision models from scratch? Essentially, should we rebuild a model and just train all of it, a nice giant convolutional neural network to do these types of things? And I hope not. So one of the first things that we can do is basically label propagation. So this is a very simple Q&A. For the HR example, could you just do a change from baseline and alarm on the delta? The range per patient seems to be constant from the plot. Let me just refocus on this. I'll go back and answer this. But yeah, if the answer is, could you do something very simple? I think that's the point. Yeah, you can definitely do some much more simple things that get a lot of value, but I will revisit your question at the end just to make sure I answer it fully. Yeah, change from the baseline. So the question is like, how do you use that baseline? Are you use the time series model as a baseline, or are you going to use, what data do you actually use to define the patient's baseline? If you use a populational baseline, the model becomes very wide and unhelpful. if you use a patient-specific baseline, it can become more helpful. And what I've come to believe is that you can use even very simple models to derive those baselines. So, but if that doesn't answer your question, feel free to post more and I'll answer at the end. Yeah, so here we are doing soft label on the training data. So the idea is that we might have these right here. And so these are labels that might come from grow operations. And then we can choose a model, have a model of your choice, whether that's a hand designed neural network or a pre-trained model or basic statistical features. And you can basically get it, you can train the model and get it to repredict on the training set. And labels from the training set that do not agree with the model predict on the training set are probably false labels, or at least outliers in some sort. And so the idea here is that we can take our own data and train the model and then run that prediction back on the same training data and identify what might be mislabels. And then we clean those labels out and retrain the data and run it again. And this is a label propagation method by which, with very little hands-on work, we can essentially clean up our own data set or get an AI algorithm to clean up that data set for us. So again, that's an 80-21 where we can get it done very quickly, not a lot of weeks and weeks of manual labeling. You can get it done pretty quickly. Another problem, it's like, well, Meta hasn't published a lettuce specific example. They haven't given us the lettuce computer vision model yet. But the idea is, we could also be using pre-trained models. So I think these are one of the coolest things that we have in AI to date for really getting a lot of benefit out of work that's already been done, these pre-trained models. And the idea is that you have essentially a feature space or an encoder, and it basically you're freezing a large part of the neural network's architecture. And what we can do then, so essentially this is the bit that we get from Meta, for example, or that we get from a Google or Hugging Face, one of those sources for models. And it's this huge the slides will be available. The whole thing's being recorded and will be up on the YouTube, so you'll be able to see it then. So basically, we have this huge complex model, but Mark Zuckerberg has already put the cash in to train that thing. And what's amazing is that essentially we could just take a linear probe at the end of one of these pre-trained models and train it to our own data. And this is literally like a single layer linear probe. And what's nice about that is that's a very fast thing to train. Both on you need a smaller amount of data because essentially all the pre-training has been done, and also it goes quickly because for the back propagation, the entirety of the model training is literally training a single linear probe. It's just training that one bit of your computer vision algorithm. It's not training all the embedded errors and things like that, transformers. All that stuff is just not in there. So basically, that I consider probably like a premium example of an AI approach, an AI 80-20 solution, where effectively we have this complex computer vision model, but we're only needing to train a very small part of it off of a very small amount of data. And you can imagine when you pair it up with a system like this, by which we can easily propagate new labels and update the model, that's quite nice. But we aren't done being lazy yet. And so there's some other things we can do. For example, we can ensemble models for R&D. So here, basically, if you're looking at a real-time model that you need deployed on the edge, you might want a smaller model, a more compact model. It's very specific. But for an R&D setting, you might actually say, we're going to get one of these, like a larger baseline model, or maybe even ensemble multiple models together. And so this might be a big clunky model, but since it's in an R&D setting, it doesn't matter. You're not really worried about the speed or how much compute it takes. So you can take essentially multiple of these encoders, and each one gets a linear probe, and then you ensemble the predictions from the linear probe into a single ensemble solution. And a final one is that that I think is interesting is that, so we were just talking about multiple labels. So effectively we have multiple species labels and it's predicting all of them at once. And the advantage of that is that we have this like cross label uncertainty. So basically if it's not sure which label it is, you can really see that in the outputs. And there's also the correlation between these. So effectively, you might be able to have different labels in understanding if certain labels are correlated with each other. But another thing you can do is that, as your number of classes grow, you can actually also do like an all versus one class. So effectively, the idea is same linear embedder before. So basically, the exact same model that we're using, pages ago. And the only thing we do is train multiple linear probes. So effectively, not much more complex than training logistic regressors on, a big hefty backend. And you can train multiple of these essentially logistic regressors and on an individual class. And what's cool about this is then you don't need to have data that are essentially have all labels. So effectively, you can have individual or bespoke data sets for each individual class in your labeler or in your classifier. And another nice thing is that as you bring in new data sets and new examples, you don't need to basically retrain the entirety of all your other class models. You can literally just train a new one from there. So effectively, instead of a new class comes in and you retrain the entire model and go from there, it's a new class comes in, you just grab the data that's relevant to that new class, train it, and the rest of your model stays exactly the same. And so I think that's a very exciting thing where effectively there's a nice 80-20 solution where, yes, you lose a little bit due to correlation between labels and a bit of cross-label uncertainty quantification, but you still get essentially this operational, this maintenance requirement is way, way lower. So essentially you can have a way more complex model that grows over time efficiently. So I think that's pretty cool. And my one final solution is this in A20. I'm just scaling a 100 terabyte database. So I'll go through this one pretty quickly because I know it's been a while. But the idea here is that the situation is that, our company is getting, several gigabytes of new data every hour. And while that's nothing for a big tech company, that's literally, they would love to have a problem that small. It's pretty big for us, for our data science team, for our data engineering team. But we still don't want to throw away valuable data that we might need later. So the data looks like this. So basically, we're getting all this plant data and it's times a lot because it's coming in. And as we deploy to more farms, this thing's going to grow exponentially. So we need to be ready. So this 80-20 solution came in a few steps, and this is just embarrassingly simple solutions. The first thing we did was prioritize. So basically, we realized that while plant health, so the thing we're trying to monitor crops, need that hyperspectral image. So the image at all these different spectra to identify whether or not the plant is photosynthesizing correctly, respiring correctly, things like that. For example, grow operations doesn't need that. You don't need a hyperspectral image to tell the difference between a tray with plants and an empty tray, or some of the there's way more there's way more sort of grow operational things than this. But the point is, you still only need RGB, and so that's actually quite useful because basically it's literally Pareto 80-20, or almost literally, where 30% RGB, so 3 channels, 3 of, for example, 10 channels, are required. The other 70% of the channels are not needed for one of these problem sets. So you've already basically reduced your problem space quite a bit. Now, having reduced that, well, we can also reduce the image size. So something very simple like image compression, and we have a metric like peak signal noise ratio, which for people who aren't familiar with peak signal noise ratio, it's literally glorified mean squared error. So like the same thing we use to look at the error of a linear regressor, you can look at the mean squared error between pixel values. And with that, we basically just see how much information we lose as we compress these images. And we can also see whether or not it affects the machine learning system. So effectively, we can look at a 100, like a 99% reduction in the storage space that's required, with a very simple metric, and just make sure that it doesn't affect the machine learning system. This is, again, there's nothing super brainy about this. It's literally just doing some quick checks to see where you can essentially compress your data. And another thing we do is we take that same metric and look at selective viewing. So essentially the idea is that if you have a baseline image right here at the top, and you look at how much it changes from each subsequent image, effectively it's a little bit like a motion detector, where we look at how much the image changes over time, the PSNR, so how much the data, how much two sequential images look different, and we only flag things when the images look very different. So effectively, that way we can collect our anomalies, like data where it looks very different. But wait until but we can now essentially go from collecting data minutely to every few hours, because we now know we have a simple metric that tells us how much the images change, and we don't need to do anything with the data in between that. So it's just a really nice way that simple way that we can chuck out data that we don't need to essentially store and keep with us. Yep. So that's it. Just as a quick thing, I'm trying to in the future have more 80-20 examples. So this time I had to go through and sort of explain the ideas and stuff. But as people become more familiar with these things, one thing I'm going to do is try to start curating more of these examples for people, where we'll have a nice rich set of 80-20 solutions where people find very efficient, inexpensive solutions to certain data science problems. And it'd be nice for us to have a library of these and start getting them classified so that people can start using them for their own work. So thank you so much for your time. I appreciate it.